Okay, Assalamualaikum and good morning to all. Okay, so for today, we have a very special guest, okay, on our side. Okay, we have Mr. Muhammad Farid, okay, is from the Cuba Lab, Sdn Bhd. Okay, how are you, Mr. Farid?
I'm fine. I'm fine. Thank you for inviting me, Mr. Haris and Masa University. Thank you very much.
Okay, just for a short introduction, okay, about our speaker today. Okay, so Mr. Farid here, okay, he has experience more than 20 years, okay, 22 years in the area of sound and vibration for simulation and testing, and also in additive manufacturing. Okay, so he's also working with the LMS International Distributors in Malaysia. And of course, beside LMS, okay, he also worked directly with the Dassault system, okay, and the Honda 3S Center. And currently, he is the current chief technical expert and also the master trainer for additive manufacturing under Cuba Lab Sdn Bhd. Okay. So for today, we are going to have a short discussion on simulation-driven design. Okay. So without further ado, let me just pass the floor to the Mr. Farid, okay, for the presentation. Okay, so thank you.
Okay. Thank you very much, Mr. Haris. Thank you very much for the introduction. Well, I guess today what we will be doing is actually introduction on simulation-driven design, specifically for the simulation side. Before we can actually go for additive manufacturing, those are one of the essential skills which I will do the presentation soon. So I think without further ado, what I will do is I will just start the presentation. Please enjoy. Sorry. Do you see my slide now? Just testing.
Yes, yes.
Okay, fantastic. All right. So I guess Mr. Harris has already uh, read my biodata about myself. So I don't think I need to explain much about myself already. Just a quick one. I have a lot of past experience on simulation and testing, and now on additive manufacturing. Okay, the agenda for today is actually essential skills for additive manufacturing, design processes, types of analysis for simulations, uh, optimization discipline, topology optimization, and additive manufacturing process flow, the industry application, additive manufacturing design challenges, lattice structures, unique for 3D printing, and another example of topology optimization and additive manufacturing. So I've actually mentioned there are 6 essential skills for additive manufacturing, or some people just call it 3D printing. If you look at these essential skills available on the slide, you can see one of that essential is the conceptualization and also design optimization. I actually already highlight that in blue color. So the rest I'm not going to highlight. So today is more on simulation driven design. So it's going to be focused on conceptualization and design optimization. Okay, let's look at the traditional design processes. Okay, if you look at this slide here, in the early stages of designing, this is the process of designing. So you actually develop a concept. So you have like concept 1, 2, 3, how many ever concept that you have, and then you will design that hand sketch. So we're talking about really traditional, the old way, and then from there you actually build a detailed design, and then you go into validation and also prototyping as well as documentation. So you have to actually have a lot of documentation, paper documentation, I would say. And then you actually go in production. So this traditional design process is a very long and tedious process. because it involves designing on a paper, prototyping, and real product evaluation and also testing. Okay, just some picture of what I would like to showcase before we have CAD software available in the market. So this is how actually it looks like before we have computer aided design to actually assist us on designing. So you can see released in 1982. So AutoCAD was released in 1982. So that's where we actually see available abundance of computer aided design software solutions. Okay. And I actually already mentioned the conceptual design. So I just want to actually give the meaning of conceptual design. What is conceptual design? So conceptual design is an early phase of design process in which the broad outlines of function and form of something are articulated. It includes the design of interactions, experiences, processes, and strategies. Common artifacts of conceptual design are concept sketches and also model. So I actually show a drone because it's got something to do with Industry 4.0. So I'm just showing a picture of many types of drones. So you can actually assume that each and every one of the drones are concept. So concept 1, 2, 3, 4, 5, 6, 7, etc., etc. Okay. Then we have the CAD design process. So with the aid of computer aided design, it actually have reduced a lot of design processes due to the fact that you are already designing it in your computer, and then you can save your file for future references and also for good documentation and for you to be able to actually see an assembly of your total products. So if you look at it, it's the same process but with the aid of computer aided design. Okay, now what is computer aided design? Okay, computer aided, I think the word computer aided already make you understand that it's aided by computer. Okay, and design, so meaning to say that you are designing in computers. So that's what computer aided design is all about. And then you also have what they call computer aided industrial design. So that is two different entities itself, but it's the same thing. You are actually doing design. So one part parametric modeling, the other part you just do freehand sketch. Okay. And I actually highlighted the CAD is essential in the introduction of CE in the future because when you have the soft copy of your model in your computer, then you can actually use this model to go to the next level, which is computer aided engineering, where you do your simulation and your analysis to find the result of your product. Is it going to fail or is it going to pass? I'm going to explain more a little bit on CE later in this few more slides. So I'm gonna now show you the process of computer aided engineering design process. So I actually show you the CAD process. Now it's actually CAD and CE process. So if you look at it, still the design iteration is available there. So I'm just gonna probably just put a laser pointer. So you see there's design iteration here. So from development concept goes to the detailed design. So this is in CAD, and then you want to validate that you go into CE. If you're not happy with the result, if it fails, you go back to design details, detailed design, and then you redesign it back, and then you go back to CE and do your simulation until you actually get the right or passing mark, I would say, for the model, and then from there you go into prototyping and also validation. So when I say validation is actually more on the testing part of the design process. Documentation, these are all, I guess, you want to keep your files in your computers and your result files. And then once you are happy with this, then we can actually go into production. Okay. So what is computer-aided engineering? I guess I've already mentioned computer-aided is aided by the computer, and engineering is more if you want to do simulation and analysis of the product that you already have designed. Okay, so a typical CE process comprises of pre-processing, solving, and post-processing steps. Okay, next slide. I just want to highlight about finite element analysis. So there's a little bit of a difference between what CAE and finite element analysis is all about. But most of computer-aided engineering solutions use finite element to actually do their own their solvings, except for I would say typical multi-body simulation, which you don't need to use finite element analysis at all. Meaning to say you don't have any mesh for your analysis. Okay. So if you look at it, finite element analysis is a numerical method for solving problems of engineering and mathematical physics. So based on the idea of building a complicated object with simple blocks or dividing a complicated objects into small and manageable pieces. Okay. Useful for problems with complicated geometries, loading, and material properties where analytical solution cannot be obtained. Okay. Finite element results are validated with either analytical solutions or experimental studies. Okay. FEA process overview. Just want to show you the process of doing a finite element analysis. You can actually see on the right slide here the analysis start, the material properties, the loading, the boundary condition, and also the mesh generation. These are actually the steps. Okay, so you actually import your CAD model into your finite element or your CE model into your finite element, and then this will be the pre-processing simulation setup. Then you go into solving. So you actually choose what type of solving you want: linear, non-linear, explicit, non-explicit. Okay, and then you do post-processing, and then you look at your result. So in that pre-processing, again, I already mentioned the analysis that you want to do. So you want to do static, linear static, linear dynamic, heat transfer, CFD, and whatever. Then you put in your material properties, you put in your loadings, you put in your bounding conditions or constraints, and then you actually go for the mesh generation. Okay. Example of a FEA process flow. So I've already showed that in the previous slide. This is roughly what you can actually see. So you put in part modeling, material properties, solution phase, you put in all the loadings and the boundary condition and conduct the meshing. And after that, once the result already finished running, you can actually display the result and do your own post-processing reporting. Okay, but roughly what it will look like, it will look like something like that in your head or you're scratching what you want to do with the model that you are doing analysis on. Okay, I've already mentioned about the types of analysis that the only one that is not using finite element is the motion analysis or multi-body simulation. The rest, I would say, mostly are using finite element analysis in their CA process. Okay, now let's go to the simulation-driven design process. Okay, with the introduction of topology optimization, you can actually see the flow process is a bit somewhat the same, but inside this design iteration, when you use topology optimization, you do not need to think about how to design your product. You can actually make a big block and then run topology optimization with the constraint and the loading that you put. The software will give you the best design for the criteria below. So you have maximize stiffness, maximize frequency, and also minimize mass. So the software itself will do the job for you instead of you trying to do your conceptual design. So you have concept 1, concept 2, concept 3, concept 4, concept 5, etc., etc. So with this software, you don't need to think about doing that. It will give you the best design for the loading and the constraint that you have provided in the software. Okay. And again, I just want to highlight the reason why it is essential is because of this advanced user of 3D printing or additive manufacturing. If you are a basic user, you only download the model from the internet and then you do your slicing on your slicing software and you print. So that's the basic user. And the intermediate user is that you design your model in a CAD software and then you slice and then you print. But for the advanced user, there is one area that they will do, which is optimize the design to make the design better in strength, width, and stress. Okay, just want to highlight that. Now, this slide here actually, I would like to actually highlight what are the optimization disciplines. Okay, if you find out there's a lot of optimization available in the market, but you need to understand what you are actually doing. So if you look at this slide here, there is this conceptual design, this concept design, where you can actually see for concept design, topology, precise, and also topography is used in this conceptual design. Okay. For design fine tuning, so I would say this is we have to actually do two topology. First is during conceptual design, and then we have during detailed design. So that's where you can actually play around with free shape, and also the sizes. All right, I've actually already mentioned what is I've already mentioned topology optimization, but I've not mentioned what topology optimization is. So in this next slide here, you can see it actually started in Berlin in 1892 by the name of Dr. Julius Wolff, a 19th century orthopedic surgeon. So if you look at that statement there, as a consequence of primary shape variation and continuous loading, or even due to loading alone, bone changes inner architecture according to mathematical rules, and as a secondary effect and governed by the same mathematical rules, also change its shapes. So that's what topology optimization is all about. If you look at the picture here, you can actually see inside it looks like an optimized structure itself. So it's not really, the model is not really solid. There is porosity in there in our bone. Okay, so this forms the basis of our topology optimization technology. Okay, I've also mentioned topology optimization. What is it all about? So most simulation tells you if a design will meet performance criteria, but topology optimization creates design that meet performance criteria. So this is a very basic, simple video here that shows that this big block here is actually the model that we want to actually design, and then we have a constraint on where we want to put the constraint and also the loading. So from there, the software will actually simulate and provide you with this optimized design. So instead of you going for each and every one concept design, the software itself will give you this design, and then you will redefine it later. Okay. Methodology of topology optimization. Okay, these are some of the methods of topology optimization. I think I do not need to go in too much in detail. I have another slide which is much bigger to understand. Okay, but if you look at this slide here, it's only showing the member size, the draw direction, if you with or without without or with draw direction. If you're doing extrusion, without extrusion, with extrusion. If you're doing casting, no hole casting, and also if you're doing stamping. So these are all the picture of going into the constraint of manufacturing with optimization. Okay. Here is actually a slide just showing a sample example of a body in white topology optimization. So you can actually see how the software works. You can actually have a body in white, and from that body in white, you can actually run optimization software and get the best design that fulfills the loading condition and also constraint conditions. Thank you. Okay, this slide here, topology optimization and additive manufacturing process flow. Okay, you can actually see here in prototyping. So you actually go for a requirement. So these are the load identification with multi-body dynamics. So if you use multi-body dynamics, you almost get the real loadings instead of actually using an assumption loading. And then from there, the topology optimization will do the job for you, and also considering all the manufacturing constraint. And then after that, you do your polynubs. I think I will not mention in this slide about polynubs because that will be going into much detail. But the gist of it is actually going into this design here and make it smoother. So that's the function of polynubs. Okay, and then we have in serial production, you will see this optimization here. And this is actually a picture of actually a 3D printed job done, and we do optimization in the solution. So there is available software that can even simulate additive manufacturing processes for metals. Okay, and I have this video here showing the whole process of topology optimization and additive manufacturing process flow. So do enjoy. Okay, a very short video of the process flow. At least you get some understanding of what you can actually do with the solution that is available in the market. All right, I'm going to go to the next slide now. So again, topology optimization and additive manufacturing. So topology optimization inherently generates design suited for additive manufacturing. So again, it's also I would say it's good to have this 3D printer available in the market now, because I believe the topology optimization design has already been in the market for many years. I guess probably 20-30 years ago. but the problem is the manufacturing processes that is constraining all the design that can be designed. But with the conventional manufacturing, you cannot actually manufacture this design that you wanted. So with the coming of 3D printing, you can actually print anything, any design. Okay, so just want to highlight that in this slide here. All right, again, mention additive manufacturing and also topology optimization. You can see these complementary technologies, right? The geometric freedom. So you have the freedom to actually design whatever you want instead of too much of a constraint on the geometry. Okay, and then it injects innovation. That's really good actually. It also has this design individuality. Yeah. So because the design is so much like nature that it has its own individuality of the model that you have already designed. Okay. And then it provides you this accelerated product development. Yes, that's for sure. Okay, because if you want to do your conceptual design, you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 concept per se, let's say. That would take a lot of time to actually design, and yeah, time consuming. So with that simulation driven design software solution, you can actually cut down on that conceptual design. Okay, all right. Again, I've already mentioned the optimization solution available can also incorporate the manufacturing processes. So if you look at this slide here, this is a bigger picture from the previous slide. You can see without and also with the maximum member size, it will actually do a different kind of optimization design. That's one. And then we have the without draw direction and with the draw direction. So these are all manufacturing processes. Okay, without extrusion and with extrusion, and no hole casting. So they don't want any hole. So that's the new design on your right here. No hole. This one is with hole. So you can actually incorporate these manufacturing processes in your optimization solving. Okay? And also stamping here. And also overhang angle. So anyone who has been playing with 3D printer, this is vital. They need to know what is the degree, the maximum degree of this overhang angle. If not, you cannot print. You have to actually put a lot of support. So this red colored model here, these are all supports. The component itself is actually in gray. Okay. Some benefits of topology optimization for additive manufacturing. Again, I've already stressed it out many times. So you can actually do cost reduction via reduced part count. Yes, reduce your cycle time. You reduce your weight. You reduce your cost. Rapid prototyping and also testing also reduce because you don't have too many conceptual design. And many companies are already leveraging the technology and expertise in topology optimization for additive manufacturing. Okay, I'm going to show you an example here. This is from EADS. If you look at it, AM and TO. Actually, AM stands for additive manufacturing and TO stands for topology optimization. So you can actually see here from 918 gram to 326 gram. So that's a reduction of 64% of the mass. Okay, so it says OptiStruct allow us to maximize the weight saving benefits of the ALM process. So this is from John Mayer, EADS Innovation Works. Another example here. So just by looking at it already, you already know that it has reduced 82% of the weight. So that's a lot of cost saving on this. I would say if I look at the picture behind, is from GE here. I think it's a it's a turbine, so turbine engine. So they actually reduce 82% of the weight for one of these component that they have. Right. Again, an example of a bicycle. Okay. So you see the process here: CAD model of sheet post design for aluminum alloy casting, and then topological optimization using Altair 9.5, then redesigned by Empire Cycle. So they redesign because they have to do the smoothing, and then from there produce a titanium alloy on Renishaw. So Renishaw is a 3D printer, metal 3D printer, uh, laser melting system. Okay, that's another example. And I think I like to actually show this next slide here, because this is somewhat something. When I was actually young, I used to skate. So now they have a new design of a skateboard. Very nice. So if you look at this slide here, it says that it has reduced for 55% of the mass of this skateboard. So let's see this short video. I think it's only probably one minute plus. So enjoy. On how what we can actually do. So again, I've mentioned with topology optimization and also additive manufacturing, you can actually do wonders. You can print anything you want. You can change the typical or conventional design that is available in the market and become something really unique for you, or for that design itself. So it's kind of wonderful when you actually have this triggering effect of topology optimization as well as additive manufacturing. All right. So the next slide, I'm actually going to show you a slide which represented the IKEA Churchill work lab. So this is a project that I did on my own, due to the fact that I bought this, and after a few years, one of the bracket fails on me. So instead of actually buying a new bracket, what I did was I redesigned the bracket. So I'm going to show you what I did and what kind of reduction and also strength that actually has happened with the model itself. Okay. So this is a picture of the original design. You can actually see the original design is located here. Okay. So that's the original part. Again, why I want to do design optimization, because it fails. And I wanted to actually reduce the displacement in the bracket. And I also want to remove the concentrated stress distributed. So I don't want to localize. I want the stress to be distributed around the model or the part. Okay, and first things first, what we need to actually do is simplify the part. So inside the software that is available, you can actually have your own CAD software available as well. That you have to simplify the model. All right, simplifying it by doing a very simple model design like a trapezium here, where you actually define this non-design space. This is where you put your constraint and your loading. So those are the area that you cannot remove the material. And the design space, this is the area where we can conduct topology optimization. So this is the brown color is the area that it can be reduced. Okay. So what I did was I actually ran an optimization software. So if you look on the left, this is the optimized design. Okay, and if you are really good in designing, you can actually smoothen this design that is available here to become really nice looking and nature like. So it's after polynomials. So I actually mentioned polynomials twice. So now I can actually mention what is NURBS. So actually non-uniform rational B-spline model. So this is what happened. So I've already redesigned the bracket, and from that bracket, I actually have reduced the maximum displacement magnitude by 50%, and I have also reduced the mass by 10%. So the goal wasn't to actually reduce the mass because it's still light. So my goal was to make sure that it doesn't fail when I actually use the model. So you can actually see the original model has too much of localized stress, whereas the optimized model very less stress around here, but only at that uh, constraint or the holding bracket there. All right, and this next slide here is just showing after we have designed and optimized the model, we actually 3D printed it. So enjoy. Okay, that's the video of the printed part. So you might wonder what kind of material I use. I use ABS because the original material is ABS. So we actually print this in ABS material in our office. And then I'm gonna show you a next slide on how it's being used. So a picture of already utilizing it. So this is a short video of it. Actually printed it. So that's the whole process of what you can actually do with the available solution available in the market. All right. Now this is another slide just to showcase what some people have been doing. So this is for AP Works. They actually designed the structure of the motorbike uh, in topology optimization solution. So they use topology optimization and then they actually printed out with a uh, metal 3D printer. Okay. Next, I'm going to show you some of the industrial application. So this is on the Airbus BA systems. You can actually see so many processes that they actually reduce. So these are all optimized components. Okay, they want to reduce mass for their components. Again, another example, liver. So they reduce by approximately 20%, and load capacity was increased by 400 kilograms. So even though they have already reduced the weight, but now they also increase the capacity of that component itself. One example. And the other example here, you can see this is the Space Luna, and also sports, composite hockey sticks. So those are the things that you can actually do with topology optimization or optimization solutions. Some more examples. So bus, commercial trucks, automotive. So, and then we also have architecture and also electronics. So the market is huge. You can actually use topology optimization and additive manufacturing in any industry that you are in. Okay. Now, I would like to also highlight the design challenges in additive manufacturing. So there are three design challenges. So first, how can a designer come up with the best possible shape? Two, how can the engineer draw it in a CAD system? And three, how to consider the new manufacturing constraint. So I think I've already mentioned number one, if I'm not mistaken. So number one, how can a designer come up with the best possible shape? I guess the solution would be topology optimization. So that's the solution one. And again, I will also mention about what is topology optimization, but this is a better picture of some understanding what topology optimization is all about. You can actually see these are the constraints, and that will be the loading, and this is how the software will actually do run the simulation to actually get the best design for this loading and the constraint that is given. So that's what topology optimization is all about. Okay. So again, technology symbiosis. So it's just to actually mention, topology optimization provides the most efficient structure for a given load condition. But for traditional manufacturing, designer always have to trade performance for manufacturability. So those are the constraints that they have. But with additive manufacturing, there are no constraint on designing. I think I've also mentioned that earlier. Okay. And then we have the second design challenges. How can the engineer draw it in a CAD system? So the problem with the conventional CAD system, it relies on Boolean operations of simple geometric entities. So drafting sometimes like this can take week with conventional systems. Okay. So just an example here. I just would like to actually show you an example of a valve block redesign. So you see here, it's actually from Nurmi VTT Technical Research Center of Finland. So they actually wanted to actually do optimization on this part here. So when they do optimization, they get this result, and then they smoothen out the model, and then they do analysis, and then this is what they got. They got an optimal fluid flow. They got 67% weight reduction. That's really, really good. And they actually didn't go at all into a CAD solution. So they actually just redesign it inside that simulation software. Okay. So that challenges solution is actually hybrid modeling, direct plus Boolean, and then the new polynerves design technology. So polynerves is now being talked about. Okay, I have a short video of how the polynomials work. So it's only 11 seconds. Please have a look. Look at it. This is how you do polynomials. Okay, once you already done that polynomials, it will become something like this. Right? If you are a designer, I think this would be easy for you. And you have to have a good graphic card for your computer to actually play around with this. Okay, and then finally it will look something like that. And from that design of your polynomials, you do your analysis. Okay, and then the other challenger is actually considering the new manufacturing constraint. Okay, so you have a type of support, downward facing surfaces, you have the angle surface, and also these are the things that you have to consider for the new manufacturing constraint that is available in additive manufacturing. Okay, I'm going to go to the next slide now. This is a slide of showing how you want to reduce your support structure. So these are some of that constraint that I have already talked about. That when you want to do printing, especially FDM types or even metal 3D printer of FDM types, also you will have this problem of supports. Unless if you're using SLS, I don't think that will be too much of an issue because SLS does not need support. So yeah, these are some of the constraints that you have to look into, consider it. Okay, and again, how to do that? Solution number 3 is by actually going on a design rule catalogs and also manufacturing constraint implementation. Okay, now next I would also like to mention about lattice structure. I think is something that is also interesting. This is a picture of some of the lattice structure model that is available in the market, and people have been doing this. And I just want to highlight this lattice structure is somewhat was already available in medical industry because they want to imitate the bone of the structure. So they already have also already ventured into lattice structure in medical. Okay. So again, process for lattice design is to emulate nature. So you do run topology optimization to determine solid and void lattice zone and then build lattice structure in the lattice zone. Okay. So this picture here showing the red in color is actually solid and the void will be in blue, and in between that those are the lattice structures. Okay. So you can actually see some lattice structure in between those. Okay, there you can actually see clearer those lattice structures distributed evenly there. So this is the again you can do optimization topology, and then after that you can do a lattice structure of the model that you have. Okay, another example here. Okay, so you see clearly those are the lattice structures. These are all metal 3D printed. Conventional manufacturing cannot do this. These are all metal 3D printed. Okay. And this slide here says that it mentions again, I already mentioned that you do two-phase optimization process. One, you do topology, and after topology, then you can actually do lattice structures. So with that, you actually reduce a lot of material waste on your model, and you reduce a lot of that. Okay. Next slide here. Just want to showcase a control arm. So concept design to lattice detail. The same picture, yes. So you do analysis on that. Phase one. But then you run the void, solid and void. I think I've already mentioned this. And then from there you can see all the lattice structure, and that will be a clearer picture of that model there. Much clearer. All the lattice structures here. These are all lattice. These are all lattice. Okay. And from there you do your analysis to look at the displacement and the stresses available for that lattice. So if you look at this topology with manufacturing constraint, blended solid lattice, the stiffness has already been improved by 12%. So that's also good. Okay. All right. Again, this is the spider bracket. Lattice design variation. Okay. I think I've already mentioned that. Just want to show you again. That's how it's going to look like. This is for lattice only design. Okay, you see all the model are all on lattice. Okay, and then this one is internal lattice structure design. So internally, you will see that there's lattice structure inside. So on the outer layer, you see like a solid, but inside is lattice structures. And the concept number 3 is the blended between the solid and also the lattice design. This is what happened. I think this is from Renishaw, materialized Altair and also Renishaw of the model that they actually have designed. This is a spider bracket, right? Not sure. Yes, spider bracket. This is a spider bracket, and that will be the last of or the concept 3 design that they actually have already choose. Okay. So from design to manufacturing. So you have design, and then you prepare, and then you build that in your metal 3D printing. Okay, that's an example of lattice and also topology. And I think I would end this presentation by showing you one more example of topology optimization and additive manufacturing. This is actually a satellite antenna holder. So this part here. So you can actually see this part here. So what they wanted to do is actually they want to reduce the weight, of course. Satellite, aerospace, they all want to reduce that because they don't want to consume too much fuel. Okay. So I guess it would be a animation video, sorry. Just showing this is the original design. All right, I'm going to show you the slide there. Again, this is a picture showing how it looks like and how is it being called. So what has happened? It has reduced the weight from 1.6 kilos to 0.9 kilos. So it's about 43%. And it even increases the natural frequencies of the model. So from 70 hertz to 90 hertz. I'm assuming this will be the first mode. Okay. And then it has also improved the static behavior, the strength, the stiffness, and also the stability of that holder, the antenna holder. Okay. So again, the process of AM. So you see baseline CAD, and then conceptual optimization, design interpretation, geometric creation, evaluation of design, geometry validation again, and then you go into manufacturing. Okay. The process is quite clear. I'm just going to show you. This is the model process, model preparation. So you can actually see the process on top. Okay. So these are the model preparation. So understand design requirement again, proper meshing, proper boundary condition, and also proper optimized definition. So you have to actually define that and what are the specifications that you want to have. So higher eigen frequency, that will be higher natural frequency of that model. Okay, hard mounted boundary condition. So those are the dimensions that is given, and the weight of the antenna is actually the load of that component itself to cater for that. Okay. Then you go into the conceptual optimization. So from there, what is your objective? So again, I've already mentioned that there's three types. So this one is the minimize mesh. So you have maximize stiffness and maximize frequency. But for this model, they want to have minimize mesh. So those are the constraints and the element density. So they actually do a lot of iteration on it. And from there, they go into the conceptual interpretation. So what do they want to do? So I don't think I want to go in detail here. And then from there you have that conceptual design. So you actually, well, it just says that the Inspire helps to realize the process of creating CAD model 3 or 4 times faster than the traditional CAD tools. So parametric modeling and traditional surface modeling techniques. So loft, sweep, these are the things that you can actually do inside the software. You can actually directly download all the native CAD software available in the market. So you can actually see there Katia, they also have SolidWorks, Unigraphics, and yeah, etc. etc. Okay, from there, that's where they printed it. So you can actually see if you are doing this. I think I've already also showed the video of how you can actually use simulation to simulate how it's going to be printed and where is the right support. So they have actually done that. So that's the optimized support available for that antenna holder, and from there they printed it out and then they do a lot of finishing, and that will be the final product. Okay, last but not least, once you already design, you still have to do testing. So in the aerospace industry, they have to do what they call sine sweep and dual or sine dual or random excitation, random control they call it. So in there, they actually run. So yeah, the first eigen frequency, which is the first normal mode, they run it in simulation. They get 91.44, but in test they get 90.9, which is really close to the real result. And then on the second eigen frequency, I'm assuming this would be either one of them will be bending or torsion mode. So one of them are bending, one of them are torsion mode. And the second eigen frequency or the normal modes is 106.9, and in test they get 107.6, which is really close. So actually they have already, I would say, success in this redesigning of the antenna bracket and using topology optimization and also additive manufacturing together. Okay, I guess that would be my final slide. do like us on Facebook. So I'm from Cuba Lab, so please do like on Facebook. And I guess I'm not sure whether we have question and answer because I'm only allowed for 1 hour live. Uh,
Okay,
Mr.
thank you so much, Mr. Farid.
You're welcome.
Actually, we got this one question. Maybe it's a
Okay,
simple. Okay, I have shared into the screen.
okay.
Okay, this is Muhammad Nazrul. He's asking, I am using AutoCAD 2007. I know about
Mm-hmm.
this version very well. Now some update version is going on. So can I continue the 2007 or I need to change for the update version? It's just for the AutoCAD.
Oh, this is for design. Okay. If you talk about design, I guess if they can read the model, I don't think that would be an issue. But if they cannot read the model, then you have to update them. Because sometimes when you have the newer version, because I have the newer version of this topology optimization software, you cannot read the old version. So you need to upgrade to actually go import your model in your simulation software. So I guess that should answer that question, I guess. Any more questions on the floor?
Okay, thank you so much. Uh, I think from the comment, we only got one question so far. Okay.
Okay.
So I think if let's say no other questions, so thank you so much, okay, Mr. Farid, okay, for that very interesting presentation, okay, and the highlight is basically your IKEA project is quite good actually. Do you have like a collaboration with IKEA?
No, 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 no. Actually, the that's a good question. Actually, I don't have any collaboration with IKEA. The only thing is I have that model, and the fact that it was broken, and the fact that I have topology optimization software and 3D printer in the office. So I said, why not? We'll do a project, and yeah, so it came out that way. And
It's
I
very
wanted to use that example on all the slides so that at least people are aware that you can actually do it on your own without actually getting too much of an expert going or behind you or going on a consulting job for that. You can actually do it on your own itself once you already understand how to use topology optimization and also additive manufacturing.
And actually, by learning all of these tools, the participant can actually make their own product. They can try test for themselves, and even they can open up, I think, a new business from them. Because of this
Definitely.
COVID situation, most of us are losing, right? Okay, so this actually can make a side income. Okay,
Yeah, yeah,
so
yeah.
I think
Definitely, definitely.
we have exceed 1 hour. So thank you so much, Mr. Farid, for
Thank you.
that presentation, and hopefully we can have another session with you. Okay, after
Okay.
this. Okay. So anything to conclude before we end our session?
Well, first of all, I would like to actually thank you, Masa University, for inviting us to conduct this live presentation. I would like to thank you all the participants who already attended this online training, I would say. And thank you so much, Mr. Faris. Haris, right?
Haris.
Mr. Haris, thank you so much for being the moderator today. And I hope you guys have gained a lot of knowledge on topology optimization and additive manufacturing today. Thank you so much. Have a nice day, by the way.
Okay, thank you. Okay, bye. Assalamualaikum.
Okay, bye bye.